Okay, welcome to ECE 6750. This is a course on linear systems theory. I'm teaching this course for the first time, so please be patient while I also understand some part of the subject that I've forgotten since I took this course about 18 years ago or something. So I have to recall a lot of stuff from 18 years ago in order to teach this class. The prerequisite for this class is graduate standing in engineering. So I presume all of you are registered for this course, and so you probably don't need any additional authorization to be able to register here. This is an in-person class. I'm going to like for all my lectures since 2018, I've been posting the videos on YouTube so that you have access to the lectures even after you retire from your career. So you can watch the videos. If you're missing the lecture or something, you can still continue to watch the video uh, wherever you are, and uh, and hopefully this will be a useful resource for you for your research, or whenever you go out and work somewhere else, you will probably be able to come back to these videos and use them for your work. I know some of the students who have taken my optimization class and stuff, and they've gone out in their company. They still come back and watch the videos because they want to brush up on some part of the optimization. So, anyways, it's a good resource to have. Office hours will be 1 to 2 p.m. in my office, Grease Lab 464. You also have access to my calendar, so you can take a look at my calendar. If there is some slot free, feel free to book a meeting in case you are not able to attend the office hours. The course text is going to be this book, Linear Systems Primer, by Ansaklis and Michel. This particular book is a standard text for linear systems. It's also available in the PDF format. So I've given the link to this book in the Carmen page, so you can download the book as long as you are on university premises. There'll be 4 homework and 4 online timed quizzes. So the homework, of course, you can submit it in class. You can submit a paper copy in class. You can upload it on Carmen. The timed quizzes will be on Carmen, so you should be able to get access to it when I upload those quizzes, and I'll definitely give you 1 week to finish those quizzes. Typically, the way timed quizzes in Carmen work is I'm most likely going to have a quiz for 1 hour long. So you'll have multiple choice questions within Carmen, and you go and whatever put your answers there, and then it will give you the score right at that point of time. So it's instant feedback. And then there is a course project where I would like you guys to look at some of the business problems prevalent in today's world that could be potentially solved using the concepts from linear systems theory. We'll talk a little bit more about the projects in the future, but typically speaking, the way I think of course project is a way to understand a particular field, an area where you want to get a job in the future, and or an area where you want to investigate in the future. So you use course project as a way to have early failures in that journey, and then you can upload whatever successes you have had. You can upload it on your GitHub profile, you can upload it on your website, you can link to it in your LinkedIn, and hopefully that will help you with your job search or with your position search for whatever next position you might be looking for. The grading policy, so I'll look at the aggregate of all of this, and then at the end of the semester I'll be curving for giving out the final grade. I expect you guys to work on your homework completely on your own. You can probably take some help of the students. So there are 2 places where you can get help. So first class of help is you can use AI tools to better understand what's being taught in the class, what could be the implications if you want a specific example, and whether that example can be solved using the topics that we have covered in the class or not. You can use AI to generate answers for that. And by AI tools, what I mean is ChatGPT, Gemini, whatever other favorite tools you might have, Claude, and so on. Now, you can also take help of your fellow students in the class. By that, what I mean is you can ask them, you can discuss the questions with them, but you still have to write your own solutions. You have to work on the assignments completely on your own. from that particular perspective, wherein you take help from whatever resources are available, including books, myself, other students, but you have to write your own solutions. You cannot really copy and paste stuff from Claude or ChatGPT directly. Uh, more importantly, if you're using AI for anything that is submitted, you must strictly mention there at that place that what all things you asked AI to do and what all things you did on your own. So that's something that has to be made clear. Ideally, you shouldn't be taking help of AI for solving homework problems, because the whole reason of homework problem is to build the muscles in your brain. And if you're using AI, then the AI is building the muscles, not you. And so the benefit will go to the AI companies and not you. So that's the whole point. The project report will be due on April 28th. And what you have to do is, you don't have to create a report, but you have to create a presentation. And if you have written codes, then you have to submit the codes for your project. So ideally, I want you to solve a real world problem using concepts from linear systems theory. So you can use Gen AI tools for conceptualizing, finding references, generating code for the project, and it should be marked as such in the project. Ideally, I expect about 25 hours of effort to work on the project and write the code, and another 1 hour for making the presentation. We are going to talk about predominantly, if you look at the content of the course, we are going to talk about linear systems theory using the state space method. So I know some of you who might be coming from research background, you're already probably using state space methods in your research. But essentially, this course builds upon ECE 3050, which is signals and systems, ECE 3551, which is feedback control systems, and then you might have taken some other signal processing courses. So linear systems theory essentially borrows, or rather makes things that you had studied earlier, it makes it more concrete, it makes it more mathematical. You understand the mathematical underpinnings of all the stuff that you have studied in those courses. Okay, so we provide a comprehensive background for the analysis of linear systems using state space methods, stability of linear state space systems, learn how to design feedback control strategies for linear systems, and then how do you do some other things like Leuenberger observer and disturbance rejections and so on in the so those are the kind of things we are going to talk about in this class. There are some other information in the course information sheet that could be very beneficial to you if in case you need further help. And that's pretty much it. Any questions on the content of this course? Or yes, please.
So you said the quizzes are going to be like you're going to give us 1 week to solve the quizzes?
Yeah, so for instance, I'll upload a quiz and I'll send you an email, or I'll announce it in the class that look, there is a quiz due on X date, and then you will have to go.
Time. Once you start the time.
Once you click on the link, then the time starts, and then you have to end it within an hour. So you can't like sort of pause the quiz, go to other stuff, and then come back and start taking it. So you only have one chance to take the quiz. Yes, please.
And the project functions is the final exam?
Yes, that's right. That's right. Any other question? Yes, please.
For the presentation, is that just like a PowerPoint type presentation?
Yes, PowerPoint type presentation. Any other question? Yes, please.
Is the quiz going to be open book or?
Open book, open notes. Yeah, open book, open notes. See, the point is, if something is open book and open notes, then those are not important. In the sense that you probably need to recall the concepts quickly enough to be able to complete the quiz on time. And so if it is, even if it is open book, how many pages are you going to read in order to answer the question? So, yeah. All right. So why are we studying this class? What's a cool application of linear systems theory? So let me start with a cool application of linear systems theory. How many of you have seen this video, 6 Minutes of Terror? No? Wow, okay. So I grew up watching this video. I've probably watched this video a million times. Oh wait, it has only 33K views, so maybe not a million times, but something of that order. Let me just increase the volume a little bit.
But its main job is to take a vehicle that is streaking across interplanetary space. These speeds that spacecraft travel are just tremendous. To get those speeds down to practically zero on the surface of Mars, we have a heat shield, we have a parachute, we have rockets and an airbag. And we have to use all those elements very quickly and get it all done in 6 terrifying minutes.
Everything we do in EDL is decided by the computer. We have different sensors that trigger different things, and there isn't time to call back and say, hey, the winds are higher than we expected, or you know what, I'm going to hit a big pointy rock that's going to hurt these airbags. It's all about autonomy. I think that's probably, in my mind, the most challenging part. It's just lack of control.
The spacecraft hits the atmosphere of Mars at 12,000 miles an hour. That's time zero for our entrance into landing sequence.
When we hit the top of the Martian atmosphere, we're moving at a speed of 25 times the speed of sound. That's like 20 times faster than a speeding bullet.
And that atmosphere is thick enough that it's going to turn the front end of that heat shield about as hot as the surface of the sun.
Hot gases have enveloped the spacecraft, and the outside skin of the heat shield will reach a temperature of 1600 degrees Celsius. This lasts for 30 seconds.
There's a huge temperature difference from the inside to the outside of the heat shield. The vehicle on the outside is getting thousands of degrees centigrade, while the inside may get up to barely room temperature.
We go through what's called the heat and deceleration pulses. As it slows down through the supersonic speeds and approaches Mach 2, we open a parachute. We're going now about 1,000 miles an hour.
So that parachute comes out, it really slows the vehicle down really fast and brings us from going almost sideways to bringing the whole vehicle almost vertical.
The Mars surface is rapidly approaching. We're still moving now about 250 miles an hour.
20 seconds after we deploy the parachute, the spacecraft has slowed to subsonic. In other words, this time it's moving slower than the speed of sound. At that point in time, we jettison the heat shield.
And then 15 seconds after that, the lander pops out and repels down a 20-meter-long bridle, a rope.
So what happens is while the lander is being lowered from the back shelf, the whole spacecraft is hanging on this cord here. And it's really about the size of a shoelace. It's not much thicker than that. So when that's done, we've got this really neat system. We've got the parachute on top, the back shell in the middle with the retro rockets, and the lander down below.
At this point in time, the radar will have acquired the surface. It'll be in lock with the surface.
And once it sees the ground with the radar, it figures out how fast it's going and how high it is. From that, it can do the math to figure out how long the rockets need to be on.
We added very late in the project a descent imager. It's a camera that takes 3 pictures and compares high contrast items in those pictures to try to determine the horizontal velocity at which we're moving across the surface to help decide which transverse rockets we're going to fire.
At this point in time, we have to fire the retro rockets, or we're going to slam right to the ground.
And just about 5 seconds before we hit the surface of Mars, we inflate the airbags in the lander, and we light the retro rockets. The retro rockets bring the whole system from about 150 miles an hour down to zero, about 15, 20 meters off the surface.
And then we cut the bridle, and the airbag falls the final distance to the surface.
And that velocity when we land is about 24 meters per second when we hit the surface. We hit hard, we bounce high.
Smack, the first impact, 40 Gs. We bounce just as high as we fell from, and then smack again, nearly 40 Gs.
It could kill it right there. The first bounce, if the rocks are in the right formation, if you hit the bags in the right way. Our system isn't bulletproof. It has Achilles heels, and if the rocks want to find those, they can.
And then bam, again and again and again. Some 15 to 30 impacts, each slightly smaller than the previous one, until finally we end our last minute in this rolling, bouncing rollout. that terminates with lander sitting quiet at 0 miles an hour on the surface of Mars. And that's it. MEL has landed. EDL is complete.
All right. So this is about a spacecraft that has to go all the way from Earth to Mars, and this sequence happens when it's entering the Martian atmosphere and then landing on the surface of Mars. As you can see, there are a lot of things that has to go on in this particular system. And what I want you to focus on is, if we were, so let's say, so this happened in 2004. This video is not from 2004, but it is about 18 years ago, right around the time when I was taking this linear systems theory course. And but this mission is about the 2004 descent of rover. I forgot which rover it is. Oh, landing of MER. So that's the rover that this video is trying to capture, like what happened. The issue is that it takes 14 minutes for any information from Mars to come to Earth. So you cannot really do any real-time improvement to whatever control algorithms are there on that particular spacecraft or on that landing structure. And so now, the thing that I want you to think about is, if we were sitting in 2000 and we were asked by someone to create the control systems for this, what are the things that we need to keep in mind? What is the first thought that comes to your mind? So this is what we have to accomplish. We are sitting in an office in 2000, in the year 2000, and we need to figure out what is it that we need to do in order to make this a reality. So what's the first thought that comes to your mind? What is it that we should do? What's step one? Yeah.
We do really basic kinematic modeling with trying to figure out, how do I know what my acceleration is, probably based on Mars. How do I know what my velocity is for my orbit, and how do we record it?
Wonderful. So you will come up with a system model, a dynamical model of this particular system. What else? So we have the dynamical model of the system, yes.
We have to make the system more intelligent and autonomous, so
Right.
it does not depend on our decision from the Earth.
Sure.
It takes a lot of time. So
Yeah.
it needs to make the decision right on spot based on the feedback.
Okay. We have to do something before that. So we have created the system model. What else do we need to do? Yeah.
Figure out what is the system model we want to control and how we want to do that. So thrusters or control wheels.
Right. So you need to figure out what are the actuators. Okay. So we have the model. Then we need to figure out what the actuators are. Anything else?
Instrumentation.
Sorry?
Instrumentation.
Instrumentation. Figure out what sensors you want to put on that particular spacecraft. Anything else?
I was going to say sensors.
Okay. Yes.
Like the stability of the system.
So this system is inherently unstable because you are entering an atmosphere. You have an unstable system. Remember what we say in 3551, what happens to an unstable system? It essentially blows up. And what does blowing up means in this particular context? It crashes into the ground. So if you don't do anything, this whole thing is going to crash into the ground. So we have to do something in order to make sure that the system is stable. In some sense, it's following a behavior that we want it to follow. Okay. Anything else? So we have done this model. We have figured out what actuators, what instrumentation we need to put, and then we need to design the control algorithm. Awesome. Anything specific you notice about this particular video? Like you probably looked at the entire video, you looked at the spacecraft. Was there something interesting in that spacecraft? We had this big mission of flying from the outer atmosphere of Mars all the way to a specific point or a specific area on the surface of Mars. And it wasn't really a single thing that was happening. It was a series of subtasks that the spacecraft carried out. So we need to come up with series of subtasks, and those tasks have to be executed at specific point of time in that mission, right? Anything else? It didn't have one thruster. It had 4 thrusters, or maybe 6 thrusters, or 8 thrusters, right? So why did it have 6 or 8 or whatever number of thrusters it had? So let me go back to the video. Let's see if we have that. I think this is the time when the thrusters are supposed to turn on. No. I'm trying to go back to that video. So this is parachute. So it's not really controlling anything in the parachute. It's just descending, decelerating at its own pace. And at some point of time, the thrusters have to come on, and I'm trying to figure out when is that going to happen. There it is. Okay. How many thrusters it has? So this video is showing 3 thrusters, but I'm assuming that there will be more. Why do we have 3? Why not 1? Why can't we just rely on 1 thruster? Yes.
You need to define your degrees of freedom, so it has presumably 1 thruster to move it left and right, forward and backwards. Well, decelerate.
Right.
So presumably not down.
Okay, so we need more than 1 thrusters, it seems, for this particular task. We can't rely on 1 thruster alone because we want multiple degrees of freedom. We want to be able to control the system in a specific manner so that it lands at a specific spot with a specific velocity, right? So it's not just a matter of picking the right spot, but it's also a matter of picking the right velocity at which it's supposed to touch the surface of Mars, right? So all of this idea is somewhat interconnected, right? So you need the instrumentation to be able to know at what is the current state of the system. Now, instrumentation will not tell you the entire state of the system, but you probably can reconstruct what the current state of the system looks like, how much far we are from the surface of Mars, using the information that the instrumentation provides. This is known as observer design, okay? And this is something that we will talk about. So if you have sensors, if you have information from the sensors, how do you figure out what the state of the system looks like? The state is used in defining the model, but the instrumentation gives you some information about the state, and you want to reconstruct the entire state. So that's where observer design comes into picture, and that's one of the major topics of this class. How many actuators to pick in order to achieve the mission? That's part of this notion called controllability of the system, and we'll talk about controllability. That's another very big chunk of this particular class. So we'll talk about controllability, we'll talk about observability, control design, right? So this is doing the math part that was alluded to in the video. So the control algorithm has to, there are 2 types of algorithms. One is the observer design, so that takes sensor and figures out what the state of the system is. And then the control algorithm, which takes the state and figures out what the actuators are supposed to do. And the control algorithm design is also something that we will do. And the series of subtasks is something that we don't care about in this particular class, because what we tend to do is somebody who's very intelligent, far more intelligent than all of us, figures out how do we define this big mission into a series of subtasks. Many a times the series of subtasks comes from the experience of the individual, experience of the organization, physics, chemistry, and so on, like a lot of different principles that comes into defining what those series of the subtask is going to be. And then we just look at the individual subtask and we try to figure out what the control algorithm should be for each of those subtasks, okay? So that's what we are, so this is something we are not going to talk about, but the controllability, observability, observer design, and control algorithm design, those are the 4 topics. That is the major chunk of this particular class. The other part that I want to emphasize, this is a 6000 level class. So what generally happens in 6000 level class is you tend to learn things at an abstraction that allows you to extend those abstraction to various different scenarios in the future. So in this particular class, we'll start with the notion of vector spaces, infinite dimensional vector spaces, finite dimensional vector spaces, norm over those vector spaces, and so on. So we are basically, lifting a 50-pound dumbbell every day, because what happens when you lift 50-pound dumbbells every day? Your muscles become strong enough to take care of 10-pound, 20-pound, and 30-pound dumbbells as well. And so that's what we are trying to build. So the first few lectures of this class, we are going to be building our muscles to be able to understand some of these topics at a sufficient generality that later on, no matter what kind of system you get into, you will have adequate tools in your tool bag to be able to do all of this observer design and controller design for those kind of systems. Okay. Any questions so far on this? We will be using modern technology of Blackboard and chalk for all the lectures. So, awesome. So let's get into the discussion. The first topic I'm going to talk about is field. Okay, so this is page 455 in the book. So I'm going to start with the appendix. So appendix has some of the preliminary materials. So we'll talk about those preliminary materials first. So what is a field? I have a non-empty subset F. I have two operations. So this is an addition operation. We won't call it addition. I mean, we can call it addition and multiplication. But generally speaking, they are just called operators. Not operators, but operations. Addition and multiplication operations. And what do they satisfy? This property is known as associative. Okay, so I have a non-empty set. I define addition and multiplication over this non-empty set. It takes two elements of the non-empty set and it outputs an element of the non-empty set. Okay. Awesome. So let's consider the interval 0, 1. Interval 0, 1, it's a closed set. It's a non-empty set. There are many, many elements within this particular set. Just assume the usual operations of addition and multiplication. Is it a valid operation? So let's say 1 plus 1, it gives me 2. 2 doesn't lie in the field F, right? The field that we wanted to think about was 0, 1. So it turns out that the usual addition and multiplication doesn't really satisfy this property. So we'll look at what satisfies this property. I mean, in particular, the space of real line with addition and multiplication would satisfy all the properties. We'll get to it in a bit. But one thing that I want to emphasize here is that if you look at the set F, the addition should output element of the set F, and the multiplication should also output an element of the set F. And the first property that it must satisfy is the associative property. So it doesn't matter. So what does this say? If I add beta plus gamma first and then I add alpha to it, I should get the same thing as if I had added alpha and beta first and then I had added gamma. So the order in which I'm doing the addition, it shouldn't matter. Same thing happens for multiplication as well. The second one is commutative property. The third one is distributive property. Let me just write the name first. Okay, so these are all the properties that a field must satisfy. Then it's a field. You can define any operation you want, which is a function that takes as input two elements of the field F, two elements of the set F, and outputs an element of the set F. As long as it satisfies all these 7 properties, it becomes a field. Then we call it a field. Okay, so field is a non-empty set with 2 operations, addition and multiplication. And it should satisfy associative, commutative, distributive property. There exists a 0 element in the field, and which if you add any element to the 0 element, you get the element itself. There should be a unitary element in the field, so that you have an element, you multiply it by to the unitary element, you get the element itself. But these two are the ones where a lot of things breaks down. So for every element, there has to be a negative element such that you add the 2 and you get a 0 element. And for every element that is non-zero, there has to be an inverse of that element such that alpha times alpha inverse is equal to the identity element. And this should hold true for every alpha, beta, gamma in F. All of these statements should hold true for all alpha, beta, and gamma in F. Okay, so I'm going to give you some examples and some non-examples of field, so that way you will understand this better. So let me write the obvious ones. R is the space of real numbers, C is the space of complex numbers. So real numbers and complex numbers obviously satisfy all of these properties. This is your bread and butter in the undergraduate ECE classes. Can someone tell me a non-trivial example of this? Let me give you a non-trivial example. The space of rational numbers with the usual addition and multiplication. So let's look at the space of rational numbers. Does it satisfy this? Obviously, it satisfies this. It satisfies this. Is 0 a rational number? It's a rational number. So 0 plus a rational number is a rational number. Is 1 a rational number? Yes. So 1 times a rational number is a rational number. For every rational number, we have a negative rational number, which the sum of the two is equal to 0. And for every rational number that is non-zero, is the inverse also rational? So is the inverse of a rational number rational? So that's also rational. I should write alpha inverse is in F. So alpha inverse should also lie in F such that alpha times alpha inverse is 1F. What about irrational number? Would irrational number satisfy this property? So let's think about it. It satisfies this, it satisfies this, satisfies this, satisfies this. Okay. There exists 0F in F and 1F in F. Is 0 an irrational number? Not really. Is 1 an irrational number? Not really. Okay, so it fails. We don't have a element 0 in the set of irrational numbers that satisfy this property. Okay. There is another place where the irrational number is going to fail. I can add two irrational numbers. And I might get a rational number. Okay, so simple thing. If I have square root of 2 and 1 minus square root of 2, are these two irrational numbers? They are. I add the two. I don't get an element in that particular field. So it's not. Irrational number is a non-example. So let me write down the not a field. R minus Q. So R minus Q is not a field purely because you can add two irrational numbers and you might get a rational number. So not quite a field. Another is a rational function. These are typically given by P of S over Q of S. P of S is a polynomial in S, Q of S is another polynomial in S. So these are called rational functions, and the set of rational functions is actually a field. So this is a polynomial, and this is also a polynomial. The polynomial could have only real coefficients or it could have complex coefficients. But as long as the numerator is polynomial, denominator is polynomial, then it's a field. Let's think about it. If you add two rational functions, do you get a rational function? Yes. If you multiply two rational functions, you get a rational function? Yes. And then it also satisfies all of these properties. Okay. This was the idea. This was the core idea in your signals and systems class and in your ECE 3551. How many of you have taken 3551 or an equivalent class, feedback control systems? Only a few people? Okay, kind of, sort of. Okay. Awesome. Okay. Another non-example, so polynomial. So just P of S. If you have polynomials in S, what's the problem? The most important problem is, of course, you can add polynomials, you get a polynomial, you can multiply polynomials, you get a polynomial. All of these conditions are satisfied. The real problem is this condition is not satisfied, which means you take the inverse of a polynomial, you no longer have a polynomial. Okay, so that's why polynomials is not a field, but rational functions is a field, because the inverse is well defined.
Professor?
Yes.
So one thing I was wondering is, wouldn't, if you just said Q of S be 1, wouldn't that rational function be a polynomial? So how does that not?
Yes. So this would become a polynomial, but the inverse of rational function is still a rational function.
Okay.
But inverse of a polynomial is not a polynomial.
Oh, okay.
So this seventh property is not satisfied by polynomials, but it's satisfied by rational functions. Okay. Any other question? Awesome. Okay. The next topic is vector spaces. So for vector space, I need two things. I need V, which is a vector space, and I need F, which is a field. So I have a vector space over a field F. I have two operations defined: addition, which maps V cross V to V, and multiplication, which maps F cross V to V. So what are the properties that it should satisfy? X plus y equals to y plus x. So I'm going to take x, y, z in V, alpha, beta, gamma in F. Okay. So we have a vector space over a field. So whenever we talk about vector space, we also have to specify the field, so that all of these conditions must hold for every x, y, z in V and for every alpha, beta, gamma in F. Let me write it here. For every x, y, z in V, alpha, beta, gamma in F. Can someone give me an example of a vector space? What looks like a vector space? So let's consider Euclidean space Rn. And what's the field? Let's take the field as R. Is that a vector space? So let's think about it. If this is my V and this is my field, is that a vector space? So addition, if I add two vectors, do I get a vector? Yes. Can I multiply a scalar to a vector and I get a vector? Yes. Sum of two vectors, it doesn't matter in which way you add. This also holds true. There is a zero vector such that if you add the zero vector to the vector x, you get the x itself. It satisfies this property, it satisfies this property, satisfies this property. If I multiply zero scalar to any vector, I get a zero vector. If I multiply one scalar to any vector, I get the vector itself, right? So that's an example. What's not a vector space? Let's say Rn and C. If I pick my field to be complex numbers, and if I pick my my vector space to be, the vector space to be Rn, then it doesn't satisfy any of the criteria, because if I multiply a complex number to a vector, I get a complex vector. I don't get a Euclidean vector. So this doesn't satisfy. So if my vector space is Cn and my field is C, then again all of these conditions are satisfied. In particular, you can always have Fn as V over F. That's always a vector space because all of those conditions are satisfied if your vector space is Fn. But mixing and matching doesn't work, okay? But if you have Fn and F, that's a vector space. If you mix and match, you may not be a vector space. So remember, we were talking about rational polynomials. So if you take n-dimensional rational polynomial, it's a vector space if your field is also the set of rational polynomials. What about polynomials and scalar? Is that a vector space? So let's say P, let me use P to denote the set of polynomials of let me say S. So my x is a function of S, and this is equal to alpha 0 plus alpha 1 s raised to 1 alpha n s raised to n. So I have a set of polynomials. How can I make that into a vector space? What sort of field should I pick so that it satisfies all the conditions for being a vector space? Assume that these are all real numbers. So let's say alpha 0, alpha 1, all of these are real numbers. So I have polynomials with real coefficient. If I pair this P with R, So this is polynomial with real coefficient. If I pair that with R, does it satisfy all these conditions? So let's look at it. Sum of two polynomials is a polynomial, yes. Multiplication of a real number with a polynomial with real coefficients is a polynomial with real coefficients, yes. Sum of two polynomials, it doesn't matter in which way you add. This one also holds. Is there a zero polynomial such that zero polynomial plus x equals to x? Yes, that's true. This one holds, this one holds, this one holds. If I multiply a polynomial with scalar 0, do I get a zero polynomial? Yes. If I multiply it by scalar 1, I get the polynomial itself. Yes. So this is a example of a field of a vector space. What else? I want to give a non-trivial example of vector space. Oh yeah. Okay. So this is the set of polynomials. Let me write another space. So C, A, B are N. This is the set of all continuous functions x from AB to Rn. So this is the set of all continuous functions from AB to Rn. AB is a closed interval, Rn is just an n-dimensional vector. So I'm going to pair this with the field F equals to R and V equals to let's see if this satisfies the definition for being a vector space or not. So I take the set of all continuous functions from a closed interval to Rn. If I add two continuous function, do I get a continuous function? Yes. If I multiply a continuous function with a scalar in a real number, do I get a continuous function? Yes. All of these are satisfied. All of these are satisfied. If I multiply 0 to a continuous function, do I get a zero function? Yes. If I multiply 1 to a continuous function, do I get that continuous function itself? Yes. So this is also a vector space. Okay. One thing that you will notice is this one. So okay, so something to think about, which we will talk about. Actually, we'll talk about it in a bit, in a few minutes. There is this n here, which tends to say how many elements am I stacking in order to create this particular vector space, right? So in this case, I have n real numbers that I'm stacking in order to create this particular vector space. Do I have something similar here, the set of polynomials of S? Remember, this n could be arbitrarily long. I could pick a polynomial that goes all the way to infinity. So in some sense, there is something weird about these sets in comparison to this set. Okay? And what we will talk about very shortly is that these are finite dimensional vector spaces and these are infinite dimensional vector spaces. Okay? So very important concept, finite dimensional vector spaces and infinite dimensional vector spaces. If I truncate the polynomial, if I only have the set of polynomials of order n, is that a vector space? So let's say Pn, I define Pn as set of all polynomials of order n. So x of s equals to alpha 0. So this is a polynomial of order n. Does this satisfy the vector space property? So let's think about it. If I add two polynomials of order n, do I get a polynomial of order n? Yes. This also is satisfied. This is satisfied. Looks like all of these are satisfied. So even Pn and R is a vector space. Okay. So there are lots of situations where we can construct vector spaces by pairing it with a field, and they satisfy all of these desirable properties that are written on the board. I'm trying to come up with something else that I can think about. How many of you know measurable functions? Measurable functions, does it ring a bell? No? Okay. So continuous functions are, continuous. Measurable functions contain all the continuous functions and discontinuous functions. But you have to have discontinuities that are benign discontinuities, not very complicated discontinuities. So of course, in real life, almost everywhere you see measurable functions because you have discontinuities that are well defined. But mathematically speaking, the set of measurable functions has a very specific way of defining the set of measurable functions. But I don't think this class would be the right class to talk about measurable functions. So let's see if I could avoid measurable functions in the future. If I cannot avoid measurable functions in the future, then I'll talk about measurable functions. But so far, I think we don't need measurable functions. Okay, there's another important example of a vector space, which is R infinity R. So R infinity is you have infinite number of real numbers. Sometimes you put a norm on this space. So we will talk about norms in a bit, maybe in the next class. But right now, this is also a valid vector space. And sometimes these vector spaces are extremely important from an applications viewpoint. So in this class, in the rest of the class, we will, rest of the semester, we'll talk a lot about these set of continuous functions. We'll go back to it many times. We'll go back to this particular vector space many times. And of course, Euclidean space. And I don't think we'll talk a lot about complex numbers, but there'll be some complex numbers at some point of time in this semester. But these are the most important vector spaces that we'll be using throughout the class. Any questions so far on vector spaces? No? Okay, linear subspaces. So I have W is a subset of V, certainly non-empty subset of V. Otherwise, there is no point of talking about linear subspace, so is called a linear subspace of V if and only if W1 plus W2 is in W for all W1, W2 in W, alpha W is in W. For all alpha in F, W in W. So a simple example of W is 0V, just a zero vector. Does it satisfy those two criteria? 0 plus 0 is equal to 0, which lies in W. 0 times any other scalar is also 0, which lies in that particular set. So that definitely satisfies the two criteria. It's actually not an interesting subspace. Let's look at Rn. Let's define EI as 0, 1, 0, 0. This is the ith position. And I'm going to define W as alpha times EI, alpha in F. Well, alpha is in R. So is W a subset of Rn? So W is a subset of Rn. The field is R. Is it a linear subspace? So if I add two vectors of this form, do I get a vector of this form? So it has a non-zero element only at the ith position, and everything else is 0. So if I add two such elements, I get an element of the same form. If I multiply it by a scalar, I get the element of the same form. So this is also a subspace, a linear subspace of Rn, of Euclidean space. Any other non-trivial subspace you see on the board? Any other non-trivial subspace? So let's see, is Pn a subspace of P? So P is the set of all polynomials, so it could have infinite number of elements. Pn is the set of polynomials of order n, so it has only n order terms. So if you add two n order polynomials, you get an n order polynomial. If you multiply an n order polynomial with a scalar, you get an n order polynomial. So Pn is actually a subspace of P. And recall that Pn is also a vector space. So it turns out that subspaces are actually vector spaces in itself. Okay, so Pn is a subspace of this. What about P? Is that a subspace of this? So let's say I have a set of polynomials from a to b to Rn. Let's just keep it at to R, okay? Is that a subspace? Can someone tell me? If the set of polynomials is a subspace of continuous functions over the interval a to b. So first of all, polynomials are continuous. Yes?
We have to specify that they're also over interval a to b.
They're also?
The polynomials
Uh-huh.
over.
Yeah, I mean, so the polynomials are generally defined over the entire real line, but definitely we want them to be defined over a to b, closed interval, for sure. Okay, so every two polynomial, I add two polynomials, I get a polynomial. I multiply the polynomial by a scalar, I get a polynomial. So this is definitely a linear subspace. Another linear subspace. So Pn is a linear subspace of P. P is a linear subspace of CAB to R. So Pn is actually a linear subspace of CAB to R as well. Okay. The reason why this idea of subspaces would be important is eventually in maybe 2 months from now, we'll talk about uncontrollable subspace and controllable subspace. So you can have a very complicated control system, and along a certain subspace you can control it in the state space. Along some other direction you can actually not control it. Okay, so it will go through its own dynamics. You cannot control it, but along certain dimension you can actually control it, and that's a controllable subspace. So this concept will become extremely important at that point of time. Similarly, there are unobservable subspace. So there are certain parts of the state space that you just cannot see. Okay, so in those cases, all of this definition will be used for defining and understanding the behavior of the linear systems. Okay, let's talk about linear independence. So I have a set of vector v. Let's say v1 to vn. These are all in v. Alpha 1 to alpha n. These are in f. When do we say that a set of vectors are linearly independent? So it's something that you might have studied both in your linear algebra class in the context of Rn and in optimization. I know some of you have taken optimization, so you would have seen this there as well. So we say v1 to vn are linearly independent if and only if alpha 1 v1 plus alpha n vn equals to 0 implies alpha 1 equals to 0, alpha 2 equals to 0, alpha n equals to 0. I think the other way automatically happens because each of these are 0. Then of course the sum is also going to be 0. But the key thing here is that if this holds, if the sum is 0, then it means that alpha 1, alpha 2, alpha n are necessarily 0. That means these set of vectors are linearly independent. What is a good example of linearly dependent vectors? So let's consider R2. Let me give you an example. So my V equals to R2, my F is equal to R. My V1 1 0 no 1 minus 1, my V2 equals to minus 2 2. The question is, are they linearly independent or are they linearly dependent? Okay, so let's see. I have alpha 1 V1 plus alpha 2 V2 equals to 0. This means that alpha 1 minus 2 alpha 2 equals to 0, and minus alpha 1 plus 2 alpha 2 equals to 0. Can I pick non-zero values of alpha 1 and alpha 2 that satisfy these two inequalities? If I pick alpha 2 equals to 1 and alpha 1 equals to 2, I satisfy these inequalities. So therefore, this condition doesn't hold. Therefore, V1 and V2 are not linearly independent. They are linearly dependent. Okay, any questions? Okay. Let's change things a little bit. Let me pick V2 to be 1 and 0. What do I get? Alpha 1 plus alpha 2 equals to 0 and minus alpha 1 equals to 0. So this means that alpha 1 is 0 and therefore alpha 2 is also equal to 0. Does it satisfy this condition? Yes. As a result of which V1 and V2 are linearly independent. Okay, that's the idea of linear independence. So two vectors, they are in completely different directions and therefore they are linearly independent. If they are in the same direction or exactly the opposite direction, then they are linearly dependent. I want to erase some part of the board. Let's come up with a non-trivial example of linearly independent vector. So let's say my V equals to the polynomials and F is equal to R. So polynomials with real coefficients. Let's say my V1 equals to 1 and V2 equals to S. Well, V2 equals to remember these are polynomials, right? So I have to write V1 as a function of S because these are polynomials over S, right? So I have these two polynomials. Are they linearly independent? So if I have alpha 1 times 1 plus alpha 2 times S equals to 0, this has to be true for all S. Let's say A and B. Then it necessarily means that alpha 1 should be 0 and alpha 2 should be 0. So therefore, these two vectors are linearly independent. I know I'm calling these polynomials as vectors, so it's sort of a new terminology, but that's the terminology we'll be using in this class. So everything is a vector in this class. You know, one cool thing about working with this level of generality is something that would be very complicated in a lower dimensional space suddenly becomes very easy and straightforward in a higher dimensional space. So this is one of those situations. You think about polynomials and you're like, okay, why are they vectors? Well, because they satisfy all those properties of being a vector space. And the second thing is, how can you talk about linear independence among polynomials? Well, technically, because they satisfy all these requirements of being linearly independent, and therefore they are linearly. You can define the notion of linear independence. You can extend this notion of linear independence of vectors that we studied in linear algebra to situations where you have polynomials, and the same concept kind of applies there as well. Okay. The other thing that I want to talk about is span of a set of vectors. Any questions so far on this one, on this side? So I know that part is easy. Yeah. Yes, please.
Can AB include 1?
This one? It can be any interval. So it could be 0 to 1. It could be minus infinity to plus. I mean, of course, I've written closed interval, so not minus infinity and plus infinity, but any subset of real line is fine. Okay, but it has to be a subset. It can't be just a single point. Any other thing? Any other question? Okay, wonderful. Span. So I have W, which is a subset of V, and then the span of W of the set W is summation alpha I Wi Wi and W I equals 1 to n. So you pick alpha in F. So you pick a bunch of scalars from the field F. You pick a bunch of vectors from the W, and then you do the linear combination of all of those sums. You get a span of W. Generally speaking, we will be looking at span of a finite. So this W set is going to be finite. Those are the ones that we'll be interested in this class. But span is a somewhat more general term, and it includes, you could have infinite sums as well here. But in this particular class, we'll only be looking at finite sums, and W will be a finite set. So that's, we don't have to get into the complete generality, but I just want to make a note here that you could have a span of a very large set as well, not necessarily finite set, but we are interested in only the finite sets. Okay, so that's pretty much it for today's class. In the next class, we'll talk about basis vectors, basis, dimension of a vector space, and then we'll talk about eigenvalues, linear operators, and then eigenvalues and eigenvectors. Thank you so much, and I'll see you on Thursday. I do have the attendance, so I'll take the attendance right after I turn off the video.